Hi, Scott. These are your day 123 notes. Today we are wrapping up polar. And in today's notes, we're going to talk about how do we find the slope of a polar curve. So we're going to be writing an equation of a tangent line to a specific point on a polar curve. And before we get there, there's a little bit of area practice. So for the first warm up, find the area between the curves r equals 2 cos theta and r equals 2 sine theta. I'll have you try this one. See what you get, and we'll go over that next time we're in class. For number 2, I want to do this one with you. It says find the area inside of r squared equals 6 cos 2 theta and outside r equals radical 3. And the reason I want to do this one with you is I want you to hopefully recall what r squared equals 6 cos 2 theta looks like. When you have an equation of this form where it's r squared and cosine of a double angle, this winds up looking what's called a lemniscate. And a lemniscate has a figure 8 shape to it. A lemniscate in cosine is a lemniscate that looks like, I would say, a somewhat traditional figure 8, where the max r values go to the left and right at 0 and at pi. Now, how far to the left and right should I go? It's actually going to be the value of radical 6. So the max r in this case is going to be the square root of whatever this number is. And I'll say pretty traditionally within lemniscates, you'll see that that's a perfect square. Certainly doesn't have to be. And we're going to compare that to the circle r equals radical 3, right? If we have a constant radius of radical 3, we know that that would just be a circle. So let's see if we can draw an accurate representation of what we have going on here. The lemniscate certainly is going to extend outside of the radius of the circle, given its max radius. So therefore, we have something that looks like this. Let's see if I can do this somewhat accurately. That's not bad for my lemniscate. Okay, and then for the circle, again, we want to sort of pick out what maybe a radius of radical 3 would look like and create a circle centered at the pole with that radius. So with that being said, what we're looking for is the area inside the lemniscate but outside the circle. So that's this region here, and that would be this region over here. Okay, so that shaded area. Okay. Once we have that marked off, like we've seen in many other examples with polar area, there's definitely a lot of symmetry that we have going on here. So we have essentially 1, 2, 3, 4 regions of equal area. So if we just find the shaded area, let's say from 0 to whatever this point of intersection is right here, right? If we integrate there and then quadruple that total, we'll get the shaded area that we're looking for. So we're integrating from 0 till, well, whatever this other value of theta is. So let's go ahead and figure out what that is by finding the intersection of r squared equals 6 cos 2 theta and then r equals radical 3. Well, really quickly, why don't I square both sides here to get r squared equals 3. This when we set them equal, 6 cos of 2 theta is going to equal 3. And therefore, cos 2 theta equals 1/2. So from there, where does cos 2 theta equal 1/2? Well, there's 2 possibilities in quadrants 1 and 4. Adjacent, hypotenuse. There's the opposite side. This angle theta across from radical 3 is pi over 3. So remember that we have a double angle in here. 2 theta would equal, something like pi over 3 and 5 pi over 3 if I was in quadrant 4. And therefore, theta is equal to pi over 6 when I divide by 2. And this intersection point over here would be at 5 pi over 6. So we can go ahead and find some intersection points, even though, this is the one that I want to be able to integrate over the bounds from 0 to pi over 6. So let's go ahead and take this intersection theta value at pi over 6 and set up our area, which is 4 times, now it's 1/2 according to the sector area formula. And then we're going to go 0 to pi over 6. All right, we're going to do the lemniscate minus the circle. And remember that when we plug this in, it's really f of theta squared minus the other f of theta squared. Notice how we already have the squared equations. So that's going to also feel a little bit different here, that when I plug this in, I'm not squaring these because they've already been squared. So it's just going to be 6 cos 2 theta. And then after that, minus 3 d theta. All right, and now that we have that there, half of 4 is going to be a 2 on the outside, and we're ready to integrate. We don't have to do any cleaning up at all there. So the integral of cos 2 theta is going to be sine 2 theta over 2. So that's sine 2 theta over 2 with the 6 on the outside. Now we have 3 sine 2 theta, and then minus 3 theta over here from pi over 6 down to 0. So let's see if we can plug in here. So we're going to get 2 times, all right, sine of 2 pi over 6, that's the same thing as sine of pi over 3. Sine of pi over 3, I can actually use this picture, is radical 3 over 2. So that's going to turn into 3 radical 3 over 2 when I multiply it by 3. Minus 3 theta, 3 times pi over 6 is going to reduce to pi over 2, so minus pi over 2. And that's just plugging in the upper bound. When I plug in 0, these actually both become 0. Sine of 0 is 0. 3 times 0 would be 0. So therefore, if I distribute the 2 across, we're going to wind up getting a total area in the end of 3 radical 3 minus pi squared units. Okay, so I like this question. I mean, it involves some fun-looking polar curves at the very start. The intersection points were relatively easy to come by as long as we account for that doubled frequency, and in the end, with some symmetry, it's a pretty easy integral for us to calculate. So hopefully that sort of made sense as I developed the process there. But if you have any questions about that, let me know next time we are together. Okay, here's an example at the top of the next page that gets into some of the new information today with the slope of a polar curve. So the question says, find the equation of the tangent line, and we want to do this in rectangular coordinates with x's and y's, to r equals 20 sine theta at 2 radical 10, and then tan inverse of a third. So remember, when we're given this information in polar, this is some coordinate r comma theta. Okay, so we want to try and figure out, what is that coordinate if we convert it to rectangular form with x's and y's, and then we'll talk about, if we know the point of tangency, how do we find the slope at that specific point? So let's sketch a picture of what we got going on real quick here. And if we have 20 sine theta as the polar curve, 20 sine theta is just a circle whose diameter has a length of 20. Okay, so therefore the center of the circle is at 0, 10. And if we're in the form r comma theta, with theta equaling tan inverse of a third, tan inverse of a third is some angle that's in quadrant 1 like this. Okay, so there's my angle theta. And I know that the distance from here to here is whatever the r value is. So this distance is 2 radical 10. And what we want to determine is then what's the x and the y components that get me to that point. So we can figure out what's x and what's y. Then in the end, we could determine the coordinates of this point in rectangular form. Well, since we're in the ratio for tan inverse of 1 over 3, if we call this height y, we know that the distance here, instead of calling it x, we can call it 3 times y, so that the ratio is now always for tan of theta, y over 3y, or 1/3. Okay, setting up the picture this way will be to our advantage to find this point of tangency, because now we can do some quick Pythagorean theorem. Y squared plus 3y squared is equal to 2 radical 10 squared. So therefore, y squared plus 9y squared equals 4 times 10, which is 40. And if 10y squared equals 40, then y squared is equal to 4. And therefore, when all said and done, y is 2. Okay. So now we have the y value of this point right here is something comma 2. To find the x value, well, x was defined as 3 times y, so therefore x would equal 6 at that location. Okay, so the point of tangency in rectangular form is 6, 2. And what we're trying to find in the end is we want to write the equation for this line right here. Let's see if I can do it, where I try and make it look like a tangent line. Okay. Not drawn to scale, but I now want to find the slope of that line. Therefore, once I know the slope of that line, we know the point that we're tangent at 6, 2, and we can go from there. All right, so how am I going to find slope? Well, I need really the rectangular equation of that circle, and then we can plug, we can find the derivative, plug this point into the derivative, and go from there. So what's the rectangular equation for what we're looking at in our circle? Well, it's a circle centered at 0, 10 with a radius of 10. So therefore, we can write it as x squared plus y minus 10 squared equals 100. And what we want to find is what's dy dx? What's the slope at any given point xy? So find the derivative 2x plus, here we need a little bit of chain rule. So it's going to be 2 times y minus 10 to the first times the derivative of the inside. Well, the derivative of y minus 10 with respect to x is dy dx. And then over here we get 0. All right, let's start isolating dy dx. So we're going to get 2 times y minus 10 dy dx equals negative 2x on this side. All right, last step, let's divide the 2 times y minus 10 over. So the derivative dy dx equals, when I divide this over, the 2's would actually cancel, right? So we're going to get a negative x on top and a y minus 10 on the bottom. All right, that's the formula for the slope at any given point on that curve up at the top. So therefore, if we want the slope at 6, 2, we can easily sub in at this point and say, okay, well, the x value is negative 6. If y is 2, we get 2 minus 10 is negative 8 for a final slope of negative 6 over negative 8, which is 3/4. So we are ready to write the equation of that red tangent line I drew at the top. The equation based on this point and this slope would be y minus 2 equals 3/4 times x minus 6. Okay, perfect. Well, the issue with this process is that it may not always be so easy to find the slope based on the polar equation that you're given in terms of converting all of this into rectangular form. Okay. So we want to develop a process that allows us to find the slope without converting into rectangular every time. And we're going to go through that process on the next page here. But this was, I would say, fairly easy to come by with some legwork up front in terms of finding some rectangular coordinates and equations. But once we get to this point, again, what if it wasn't that easy to convert to rectangular and get there? Well, as it turns out, it is not as easy if we have r equals f of theta to find the derivative by just saying it's df d theta. Okay, it would be nice if it was. But let's consider the previous example that we were just looking at. We had in the last example that r equals 20 sine theta. And what if I said to find the slope at pi over 3? So what I'm going to do right now is convince you that this is actually a true statement. Because I think some people are like, oh, Mr. Raleigh, you know what? I really feel like I could just find dft theta and I'll be fine. Okay, here was 20 sine theta. All right, theta equals pi over 3 might be like, let's say, this point of tangency right here. So therefore, I'm trying to find the slope, which here's the slope at that point of tangency. Okay, so what would dr d theta be if we have 20 sine theta? Well, it would just be 20 cosine theta. And if I evaluate that at pi over 3, we're going to get a nice answer because cosine of pi over 3 is a half. So 20 times a half is 10. Okay, so the slope at pi over 3 is 10. Shouldn't it be negative? Okay, so this is proof that, yeah, we can't just find dr d theta, plug in the value we're trying to find the slope at, that angle, and go on our merry way. There's a different process to finding slope of a polar curve. And it relies on some of the rectangular conversions that we have with x's and y's in polar form. So I'll have you recall that in polar form, if we set up a right triangle, we have the conversion that x is equal to r cosine theta and y is equal to r sine theta. Okay, those are good polar form conversions to know between polar and rectangular here. And therefore, if we want to calculate dy dx, we can calculate that by doing dy d theta and then over dx d theta. Well, what is that going to look like if I have something of the form r sine theta? Remember that r is going to be a function f of theta here. So what we really essentially have is if this is some function f of theta, we have a product rule with sine theta. Similarly over here, this is going to be a product rule with cosine theta. So when we go to find the derivative dy d theta, it would be something like, well, the derivative of sine is cos, so it's going to be r times cos theta plus, well, the derivative of r is just r prime sine theta. Okay, and then on the bottom, similarly, derivative of cos is negative sine, so that's going to be negative r sine theta plus r prime would get multiplied by cosine theta. Okay, and in the end, according to the product rule, this is what the general form is for the slope of a polar curve. Okay? You do not need to memorize this. I mean, if you're a true memorizer and you're like, nope, I got it, then that's fine. But we're going to develop this within each example individually. It should make sense to us that when we do x equals r cos and y equals r sine, that finding these derivatives just naturally imply that we're going to use the product rule. So let's see if we can actually go to the previous example and find the slope using polar form and not necessarily converting to rectangular. So again, in that previous example, just as a reminder, we were looking at r equals 20 sine theta. And we were trying to find the slope at the point 2 radical 10, comma, tan inverse of 1/3. All right, so in this example, let's go ahead and write that x equals r cos theta and that y equals r sine theta. And what I'm going to do is I'm just going to plug in r as 20 sine theta in both of those spots. So over here we get x equals 20 sine theta cosine theta. And similarly over here, if I plug in 20 sine theta, this one 20 sine theta becomes 20 sine squared theta. So that's kind of nice. Okay. From here, the only thing I'm going to do to clean this up a little bit, and this is not necessarily a substitution you have to make, although I think it does make life a little bit easier. If you recognize, this is actually a form of the sine double angle formula, right? If you have 2 sine cos, that's sine of 2 theta. So right now we have 10 times 2 sine cos. So this is going to be 10 times sine of 2 theta. So maybe that just looks a little bit cleaner. It might be easier to calculate that derivative in the end. Okay. All right, let's go ahead and start finding the slope. So dy dx would be dy d theta over dx d theta. Okay. Dy d theta here would be, we need a little bit of chain rule there. So it's going to be 2 times the 20, which would be 40. Sine theta times the derivative of the inside is going to be times cosine theta with chain rule. And then for something like 10 sine 2 theta, derivative of sine is cosine of 2 theta. But again, think about chain rule. We're going to have to multiply the outside by 2. So now we have a 20 cosine of 2 theta. Okay. Well, we want to evaluate this at, well, first of all, those reduce to 2. We want to evaluate this at theta. Well, what is theta, though? Remember from that point at the top, this is of the form r comma theta. Theta is some angle that has the relationship to tan inverse of a third. Now, as it turns out, theta is not a special angle. It's not pi over 3, pi over 6, pi over 4. But what we can generate for ourselves really quickly here is if we draw this picture with angle theta, we know tan is of the form opposite over adjacent, 1 over 3. And with some quick Pythagorean theorem, we get that that length is radical 10. So using this picture, we can now plug in the ratios for sine theta, cos theta, and oops, we're going to have an issue down there, but we'll fix it. All right, so what do we got here? 2 times sine theta. Well, sine theta opposite over hypotenuse would be 1 over radical 10. Cos theta would be 3 over radical 10. So there's the numerator. All right, denominator cos 2 theta. The issue is, well, we don't have what double this angle is. We only have theta. So we will have to make a quick double angle substitution here. I'm going to choose to replace it with cos squared minus sine squared. If you have another double angle that you like to replace that with, go for it, because we've talked about other options there. All right, so what was cos theta? That was 3 over radical 10, so squared is now 9/10. And then sine theta, 1 over radical 10 squared is 1/10. So let's see what we got. Top 2 times 1 times 3 is 6. Radical 10 times radical 10 is 10. Bottom, 9 minus 1 is 8 tenths. Is this starting to look familiar? 6 tenths over 8 tenths is 6 eighths, better known as 3/4. Okay, so the slope of this polar curve at this location right here, 2 radical 10, tan inverse of a third, is in fact 3/4. Okay, and that's what we found in the last example by converting to rectangular form. So we will get more practice with slope of a polar curve, but again, you don't have to memorize this formula. You do have to know these two replacements for x and y in rectangular form. And then it's all about using some product rule, maybe some chain rule to be able to find those derivatives, dy d theta, dx d theta, and then plug in your value of theta. Okay. If it's not a nice value of theta, draw the picture and go ahead and use the ratios from over here. The last question in the notes today, of course, I'll leave for practice because it is a good AP question from good old 1993. So we'll save this for class. But this is kind of a good assessment as to where you're at with polar. So given this polar curve, can you sketch it? Can you visualize what this looks like? Find the area of the region inside, and then find the slope of the curve at the point theta equals pi over 4. So if you can do all these pieces, like these are the main components of what we've seen so far in our unit on polar. So we'll do that next time we're in class together. And that is it for today's lesson on slope of a polar curve. Have a great rest of your day.